Consider a continuous beam with fixed ends on both sides and two internal rollers. The degree of indeterminacy for this beam is 5, which means we have 5 extra support reactions. In force method, we know the number of compatibility equations required equals to the degree of indeterminacy. When the degree of indeterminacy is high, it will be complicated to solve it using force method. Alternative to force method, we may use slope-deflection equations to solve for the internal moments. Then, we proceed with determining the support reactions using those moments. Let's get started. First, we set the moment in clockwise direction as positive. Then, for each span, we assume its internal moments are acting in positive direction. Up next, we need to choose the suitable slope-deflection equation to aid us in analysis. There are two different equations. The first equation is applicable to the span where internal moments present at both ends. The second equation is applicable only to span with thin far end, where internal moment is present only at one end. Let's identify the type of each span. For span AB and CD, we regard them as end span with far end fixed, where the internal moments are expected at both ends. For span BC, it is regarded as internal span. In this case, all 6 unknown internal moments can be determined using the first type slope-deflection equation. We will now construct the internal moment equations. When we are focusing on span AB, internal moment at node A is having a subscript of AB. This denotes when we are at node A of this span, our near end is A and far end is B. When introducing the slope-deflection equation, we substitute the subscript n, which represent near end with A, and subscript f with B. At this point, we produce 6 slope-deflection equations, one for each unknown internal moment. In the slope-deflection equation, the unknown fixed end moment can be calculated using readily available formula based on the support condition and loading type. Since end moments present at both ends, we may regard all spans as fixed end beam. Therefore, we can adopt the Fem formula applicable to fixed end beam with uniformly distributed load. Note that the moment determined using Fem formula is acting in opposite direction, in which the left-hand side one acting in counterclockwise direction. Therefore, it should bear a negative sign to match our convention. After calculation, we can replace the respective unknown Fem in slope-deflection equation with our answers here. Now, in these equations, the parameters that are unbeknown to us are the near and far ends rotation, as well as span and displacement. The span and displacement is usually due to the support uplift or settlement, which is not presented in our case. Therefore, we can eliminate the terms. The boundary condition of beam span governs whether the beam end rotation presents. For the ends connected to fixed support, we are good to assume the rotation as 0, since it does not allow it. For this reason, theta A and theta D are eliminated. For theta B and theta C, there are non-zero unknowns since internal roller does not refrain rotation. After eliminating non-existent terms, we can now simplify our internal moment equations before proceeding to solve them. We are now having two unknowns, namely theta B and theta C. Therefore, we need to build two equations that contain these terms before we can solve them. Equilibrium equation at each node is our way to go. Let's find out. and not B, the sum of moments MBA and MBC should be 0. Therefore, we can sum up the simplified slope deflection equations for respective internal moments and simplify the equilibrium equation again. Same goes for node C, where MCB and MCD should cancel out each other to achieve moment equilibrium at this point. We can now solve the simultaneous equations to obtain theta B and theta C. We solve the equations using conventional method. If you are interested, you may try to solve it using matrices, although the process might be more complicated than you think. After solving for the unknowns, we can substitute them back and obtain the values of internal moments. To solve for support reactions, we need to identify the shear force at both ends of beam span first. For span AB, shear force at node B is determined by taking moment equilibrium at node A. Then, by taking equilibrium in y direction, we can solve for shear force in node A as well. For span BC, since it is symmetrical, we know the shear force at node B and C are equal. Using equilibrium in y direction, we know they are equal to WL over 2. Span CD is the mirror of span AB, since the entire beam is symmetrical. With the calculated shear forces, we can calculate the vertical support reactions by summing the shear forces at respective locations. The moment reaction at fixed ends equal to the internal moment at those points. Again, the beam is symmetrical and therefore, we should obtain symmetrical reaction forces as well. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.